Hello friends, so today we are going to learn the multivariate time series analysis. So there are multiple models which are considered in time series analysis, specifically while in the domain of econometrics and financial analysis. But for the sake of this tutorial, I am just considering the vector autoregressive model. So let me write it. So vector autoregressive model is a very popularly used model in econometrics and both in advanced time series courses you can say it. So before starting it, let me explain what is time series modeling. So I think we all are familiar with the nature of series. So let's say I have a sequence or series of random variable. Let's say xi is a random variable, and I have a series of xi. When you can see letter x1, x2 till let's say xn. So I have series of random variable, but we call this series as a stochastic series when the random variable is indexed by the time. So xi is nothing but our observation or the random variable occurring at ith time. So whenever we have series or sequence of random variable which is indexed indexed by the time, we can say that this series is called as a stochastic series, or in generally we also call this as a time series. So time series is nothing but the analysis of this type of stochastic series or stochastic process where random variable is nothing but indexed by our time sequence. So xi is nothing but our univariate stochastic process. So when we are considering, let's say, a multivariate time series, then we have multiple such stochastic processes. So now instead of having just a single univariate series. Now we have a vector of this series. So we can easily write this as a, let's say, uh, RT, which is the very prominent motion, and we can write this as well. Let's say R R1T is my univariate series at time t. R2T is my second univariate series. Till let's say I will just consider RKT. So this is nothing but a combination of individual univariate series. So we have already explained the terms of stationarity uh, and how weak stationarity and strong stationarity is in play while studying the univariate time series modeling. But while studying the multivariate time series modeling, it's very difficult. As you can see, let's say this is my univariate time series. So I'm assuming that I have constant mean across all, and I have constant variance, which is generally considered as time invariant. So such properties are also extended to the multivariate setting. So first we will start uh, discussing, let's say, uh, those few properties which are widely explored in the setting of multivariate time series analysis. So first one is weak stationarity. Okay. So now when I have series, multivariate series, let's say a vector R, RT, which is a combination of uh, univariate time series of, let's say, a dimension, total dimension of P. Okay. So for weak dimension, as we have already discussed that the mean is time invariant. So we can say the mean of RT, let's say the mean of RT should be some constant. Okay. So the mean of, let's say, uh, if I'm considering a series something like this, okay, and one more series, let me add one more series for our convenience, and I will add a third series also, let's say. So when I'm saying that the mean at a point is constant. So I am saying that this mean at this point, mean at this point. So this is constant across the space. So you can, so, matlab, you can generally interpret as the mean, the trend is taking place in a dynamic order. So the all time series are moving around the mean of each other. So that's what our mean is. And we also have something our covariance matrix which we define in our multivariate setting. So it is denoted by the gamma 0, and it's defined as the expectation of RT minus mu into RT minus mu dash. That is the transpose. So this is the general formula of covariance matrix. So obviously it will have a covariance matrix structure with all the term. I think it will be P into P matrix. So because we are considering the P lengths, P time periods. So we have constant mean, and also there is a finite covariance matrix exists. So now with a k dimensional mean vector and k into k dimensional covariance vector. So this is so as you can see, this is our covariance matrix denoted by gamma, and you can see all our diagonal elements are nothing but our, let's say, variance of our I and j element. Okay, so this is I and this is j. So this will be our, let's say, variance of I and I variance, and this is generally uh, so this is generally called as a concurrent, or you can say the current also. So this is a concurrent variance of the variables here. So based on these two things, that is our mean vector and the calculated covariance variance matrix, now we move on to calculate our cross correlation. Cross correlation matrix, that is CCM. It's also called as CCM. So for in CCM we consider our various covariance, that's our k into k diagonal matrix. We take the diagonal, that is k into k diagonal, and then we uh, try to standardize it. Okay, so generally the Cholesky decomposition is used to calculate, let's say, rho 0 is equal to the rho of ij, that in concurrent relationship with 0, generally calculated the diagonal inverse of the diagonal matrix multiplied by the covariance matrix multiplied by the inverse of diagonal matrix. So this is how we calculate our rho 0. That is nothing but our cross correlation at length 0. So this is nothing but our length 0. So you can clearly see that we have calculated the cross correlation in our log 0, and this is how we calculate. So now friends, let's consider we have two series, something like this, and we so in cross correlation we are trying to find the correlation between these and the this. That's it, our series 1 and our series B. So what it does, it first it tried to find out the concurrent, that is the with first leg. Then it tried to find first leg, the first of, like, let's say, the observation at t from series 1 and observation at t minus 1 at series 2. Similarly, it happens here, let's say, t minus 2, t minus 3, t minus 2. So it tried to find the correlation between all the observation at t into, let's say, t minus something I or something. Your value of I can range from 0 to 3. when your I is zero, that is when you are finding out the cross correlation between the series of observation at time t and here at time t. You can you can call it as a concurrent cross correlation, and it has some properties. Obviously, the formula is very simple and given as that standard formula, that is of correlation coefficient. So that is covariance upon I from j upon variance of I and variance of jj. It is and the standardization, which is a simple formula. We are continuing with this with the same formula. So that's all for now. So we have studied so far